Hello, I am Geeta Babu Singh, welcoming you all again to this session. In previous session, we discussed the redundancy and checksum. In today's session, we discuss on single bit error correction. Let's start. To detect or correct errors, we need to send redundant bits. In error detection, the receiver needs to know only that the received code word is invalid. The sender adds redundant bits through a process that creates a relationship between the redundant bits and actual data bits. The receiver checks the relationship between the two sets of bits to detect or correct the errors. The ratio of redundant bits to the data bits and the robustness of the process are important factors in any coding scheme. So as we discussed in redundancy, we know that redundant bits is nothing but it is extra bits which is added to our data which we want to send. So let's repeat, in error detection, the receiver needs to know only that the receiver received code word is invalid. Received code word is invalid. The sender adds redundant bits through a process that creates a relationship between the redundant bits and the actual data bits. The receiver checks the relationship between the two sets of bits to detect or correct the errors. The ratio of redundant bits to the data bits and the robustness of the process are important factors in any coding scheme. The following two conditions are met. The receiver can detect the change in the original code word. The receiver has a list of valid code words. Second point is the original code word has changed to an invalid one. Third, figure below shows the process of error detection in block coding. Let's repeat. In the following two conditions are met. The receiver can detect a change in the original code word. The receiver has a list of valid code words. Second point is the original code word has changed to an invalid one. Figure below shows the process of error detection in block coding. Up to now we studied a redundance bit. And what is checksum? In redundance bit, we are adding the extra bit to our message. In block coding, what we are doing here, the receiver has a list of valid code words. And second is original code word has changed to invalid one. Let's understand by studying this slide, in which we have a sender block and the receiver block. The sender block consists of data word which goes to generator, then code words, then unreliable transmission goes to receiver block in which we have code word, then to checker, then to data words. In this figure, what we are doing is the sender block creates code word out of data words by using a generator that applies the rule and procedure of coding. Each code word sent to the receiver may change during transmission. If the received code word is same as one of the valid code words, the code word is accepted. If code word is accepted, the corresponding data word is extracted for use. If a received code word is not valid, it is discarded. However, if the code word is corrupted during transmission, but a received word still matches a code word, valid code word, the error remains undetected. This type of coding can be detected only single errors. The two or more errors may remain undetected. Let's repeat. The sender creates code word out of data words by using a generator that applies rules and procedure of encoding. Each code word sent to the receiver may change during transmission. If the received code word is same as one of the valid code word, the word is accepted. The corresponding data word is extracted for use. If received code word is not valid, it is discarded. However, if the code word is corrupted during transmission but the received word still matches a valid code word, the error remains undetected. This type of coding can detect only single errors. Two or more errors may remain undetected. Let's know what is block coding. In block coding, we divided our message into blocks, each of k bits, called data words. We add our redundant bits to each block to make the length n is equal to k plus r. The result n bit blocks are called code words. Let's repeat. In block coding, we divide our message into blocks, each of k bits, called data words. We add our redundant bits to each block to make the length n is equal to k plus r. The resultant n bit blocks are called code words. We have a set of data words, each of size k, and set of code words, each of size n, with k bits. Let's repeat. We have a set of data words, each of size k, and a set of code words, each of size n, with k bits. We can create a combination of 2 raised to k data words with n bits. We can create a combination of 2 raised to n code words since n is greater than k. The number of possible code word is larger than the number of possible data words. The block coding process is one-to-one. One-to-one, the same data word is always encoded as the code word. This means that we have 2 raised to n minus 2 raised to k code words that are not used. In this slide we have the block diagram of a code for error detection, in which in one column we have the data words and in another column we have the code words. When the data word is 00, for 00 we have the code words 000. When 01, the code word is 011. When data word is 10, the code word is 101. When the data word is 11, the code word is 110. If we want to send 01, we code it as 011. If 011 is received, no problem. As we told, a single bit error detected. But what happen if we received if we received 001 error detected? Here one bit is corrupted. What if 00 is received, error corrupted but not detected? Here 2 bits are corrupted. Let's repeat. In this slide we have a table in which one column is for data word and other column is for code words. In data words we have 00, 01, 10 and 11 series, and the code words are for 00, then 011, again 101 and 110. Let's see what happen if we send the data word 01. We need code for 11, for 01 as shown in table. We have the code as 011. If 011 is received, then no problem. Again, what happened if we received 001, error detected? Here one bit corrupted. And if we received 000, error corrupted but not detected. Here 2 bits are corrupted. In this slide we have again a code for error correction, in which again we have the table. One column is for data word and another column is for code words. If the data word is 0, then code word for that is 00000. If it is 01, then the code word is 01011. If 10, then 10101. If 11, then the code word is 11110. Let's say we want to send 01, we then transmit 01011. What if an error occurs and we received 01001? If we assume one bit was in error, we can correct. Let's repeat. Let's say we want to send 01 data. For that 01, we have the code word as shown in this table, that is 01011. Then we transmit 01011. If an error occurs and receive 01001, if we assume one bit was was in error, we can correct it. Let's see what is linear block codes. Almost all block codes used today belongs to a subset called linear block codes. A linear block code is a code in which exclusive or addition model 2 of two valid code words create another valid code word. Let's repeat. A linear block code is a code in which the exclusive OR of two valid code words creates another valid code word. Let's say simple parity check code. A simple parity check code is a single bit error detecting code in which k bit data word is changed to n bit code word where n is equal to k plus 1. The extra bit called the parity bit is selected to make the total number of ones in the code word given. Let's repeat. What is parity check? What is parity check code? A simple parity check code is a single bit error detecting code in which k bit data word is changed to n bit code word where n is equal to k plus 1. The extra bit called the parity bit is selected to make total number of ones in the code word even. In this slide we have a simple parity check code in which we have the 4 columns, that is data words, code words, again data words and code words. For the data word 0000, code word is 00. For 0001, data code word is 00011. For 0010 we have 00101. For 001 00110. For 0100 01001. For 0101 01010. For 0110 01101. For 0111 01111. For 1000 11001. For 1001 10010. For 1010 10100. For 1011 10111. For 1100 11000. For 1101 11011. For 1110 11101. For 1111 1110. Let's see, in this slide we have the encoder and decoder for simple parity check code. In this slide we have one side is the sender side and the other one is the receiver side. In sender side we have data words that is denoted by A, A3, A2, A1 and A0 and generator. Again code words A3, A2, A1, A0 and R0. That R0 is nothing but the parity bit. In a receiver side, we have data words, that is A3, A2, A1 and A0, and the decision logic, and then the checker side, and the code word is B3, B2, B1, B0, Q0. When we send the data word, it goes to a generator where it's generates and the generator generates the code, or it has an algorithm which has its algorithm only. Then it's sent to code word where it added its parity bit to the message. Then it goes to a unreliable transmission where it goes to code word, in which we have B3, B1, B3, B2, B1, B0 and Q0, which goes to checkers, in which it checks and then goes to decision logic where it takes the decision whether the received message is accepted or not. It checks, then it when it say valid, then it accept the message, go to code data word, that is A3, A2, A1 and A0. If it is discard, then it goes to discard. Let's look at the same transmission scenario. Assume the sender sends the data word 1011. The code word creates from this data word is 10111, which is sent to the receiver. We examine 5 cases. First one is no error occurs. The received code word is 10111. The syndrome is 0. The data word 1011 is created. In second step, one single bit error changes A1. The received code word is 10011. The syndrome is 1. No data words is created. In the third step is one single bit error changes or not. The received code word is 10110. The syndrome is 1. No data word is created. In step 4, an error changes or not and send a second error changes A3. The received code word is 00110. The syndrome is 1. The data word 0011 created at the receiver. Note that here the data word is wrongly created due to syndrome value. Fifth step is 3 bits A3, A2 and A1 are changed by errors. The received code word is 01011. The syndrome is 1. The data word is not created. This shows that the simple parity check, guaranteed to detect one single error, can also find any odd number of errors. Let's know, a simple parity check code can detect an odd numbers of errors. So once again repeat the example, that is example 10.12. in which we assume that sender sent the data word 1011. The code word created from this data word is 10111. So we have the data word that is 1011. The from the single parity check code 11011, the code word is 10111. So we know from the table. Let's simplify this problem. To create to the code word created from this data word is 10111, which is sent to receiver. We examine 5 cases. First one is no error occurs. The received code word is 10111. The syndrome is 0. The data word 1011 is created. In this second step, what we did, one single bit error changes, and that is A1. A1, the received code word is 10011. We created the code data word is that is 10111, but in the second step what happens that a single bit error changes, that is A1. Therefore we have 10011. So as seen from the example 10.12, we can see clearly one bit is changed. The syndrome is 1. No data word is created. One single bit error. Third point is one single bit error changes R0. R0, which is in the center side. R0. The received code word is 10110. The syndrome is 1. No data word is created. In fourth step, an error changes R0 and a second error changes A3. Again the A3 changes. Therefore, the received code word is 00110. The syndrome is 0. The data word 0011 is created at the receiver. Note that here the data word is wrongly created due to the syndrome value. 3 bits A3, A2 and A1 are changed by errors. The received code word is 01011. The syndrome is 1. The data word is not created. This shows that simple parity check guaranteed to detect one single error can also find any odd number of errors. Therefore, a simple parity check code can detect an odd number of errors. Thank you.